Hello, my name is Wiley Evans. I'm a research scientist at the Hakai Institute in British Columbia, Canada. And I'm calling in today from Campbell River on Vancouver Island. I would like to gratefully acknowledge that I'm on the traditional territory of the Likwita and Comox First Nations. Today, I'm going to talk to you about a paper that we're submitting to the journal Biogeosciences that will hopefully be in discussion in the next few weeks that details marine CO2 system variability along the inside passage of the Pacific Northwest coast of North America as determined from an Alaskan ferry. For those who don't know, the Inside Passage is a coastal route that connects Washington State with Southeast Alaska. It's a region known to be vulnerable to ocean acidification. It's also a region that historically has had low data coverage. And so our work with the ferry service in instrumenting this vessel, which is the motor vessel Columbia, is aimed at addressing this knowledge gap in this important region. The ferry transit represents the longest instrumented ferry run in North America, covering roughly 1,600 kilometers. This was made possible through partnership with the Alaska Department of Transportation and with funding from the Alaska Ocean Observing System, the Alaska Coastal Rainforest Center, and the Tula Foundation. The images on the right show the extent of the ferry transit covering Bellingham, the B in the south there in Washington State, up through the Salish Sea, which is the enclosed waterway on the east of Vancouver Island, the VI marked on the right panel, and mainland British Columbia, up through the narrow passageway on the northern side of Vancouver Island, which is Johnstone Strait, through the central and northern British Columbia coast and up into Southeast Alaska, the area known as Alexander Archipelago, and as far north as Haines and Skagway. The color in the left panel and on the right panel are the salinity and chlorophyll variability, respectively, and they're meant to highlight how dynamic this coastal region is. The data collected from the ferry truly illustrate this point. What I'm showing here is the temperature and the salinity on the left, as well as oxygen and PCO2 content on the right. Just want to orient you to each figure. The y-axis is latitude, the x-axis is longitude, the z-axis is time. We're going from November 2017 to September 2019. There's 2 years of data or service periods for the ferry shown in this record. Each colored line is one transit, from Bellingham up to Southeast Alaska. There's 135 transits represented in this time series. What we see is really dominant seasonal cycles. So seasonal warming, seasonal increases in freshwater input that are regionally focused, seasonal changes in oxygen content, and seasonal drawdown of CO2 in particular areas. This seasonal cycle is the dominant mode of variability, and its amplitude is really dependent on the roles of tidal mixing, net community production, and freshwater input, as we describe in our paper. Just to contrast 2 of these regions, in the Salish Sea, net community production is very positive during the growing season, and we have oxygen production and CO2 drawdown that is quite pronounced. And so there's a large amplitude in the seasonal cycle in this area. Just to the north of that, in Johnstone Strait, you'll see the area is persistently high PCO2. This region is dominated by tidal mixing. And so it's an area of active ventilation of deep water through the year. And so oxygen content is low, the temperatures stay cool, and the CO2 content stays high. Up in the northern reach of the transect, we have the area impacted by glacial melt, and you can see the big change in salinity in this region. This is where salinity changes the most. There's an interesting feature here where that salinity change actually reduces oxygen content from the peak that happens in spring, associated with the spring bloom. However, because that meltwater is cold and the alkalinity to total inorganic carbon ratio is pretty unique in that meltwater, the PCO2 content stays undersaturated despite that freshwater input. So large variability dominated by a seasonal cycle and dominated by the roles of tidal mixing, net community production, and freshwater. We can characterize regional extremes. In order to do this, we apply regional alkalinity-salinity relationship, and then we consider extremes based on variability and severity. Panels on the top show the pH variability, the severity, and the severity timing. Panels on the bottom show the same for aragonite saturation state. When we consider variability in these two parameters, there's very strong regional similarities. However, when we consider severity, there are differences related to glacial melt input in the regions to the north. We can see this very clearly when we look at where the most severe saturation state conditions are. Those are in the most northern region of the transect. That's an area known as Lynn Canal that experiences the largest glacial melt input and change in salinity, and pH in this area does not reach a correspondingly severe state. The most severe pH conditions are actually further south in Johnstone Strait in the area of mixing. We look at the timing of these conditions, and this reflects this as well, that most severe saturation state conditions occur in August in conjunction with the peak freshwater input, whereas the timing for most severe pH conditions in Johnstone Strait occur in September, coinciding with periods of highest PCO2. We think this comparison of variability and severity and the timing actually has biological implications in terms of exposure histories in two ways. One could be related to the match or mismatch of the occurrence of vulnerable life stages in the water column and adverse conditions. And this may be most important in Alexander Archipelago in areas influenced by glacial melt, where we have most severe conditions in summer and we could have occurrence of vulnerable life stages at that time. The other is in potentially with adaptation trajectories, where organisms that are residing in Johnstone Strait are experiencing a stable yet more persistently adverse environment in terms of severe pH and saturation state conditions, and may have a different adaptation trajectory than organisms that are living in Southeast Alaska and are experiencing higher variability. We map both of these regions with this time series in order to help future biological studies investigate these questions. The variability, assessing the variability allows us to consider ways to optimize the observing efforts. And we do this by calculating a term called the time of detection, which is the time required to resolve a long-term change from the noise in an environmental data set. Here we characterize the noise as the standard deviation of deseasonalized PCO2 anomalies. That's shown on the left. The calculated time of detection is shown in the middle. And you can see areas where the noise level is very low, which is also consistent with the areas where pH and saturation state variability is very low. We have a very short time of detection. And so if our goal is to track long-term change, it would make sense to put instruments in those regions such that we might have a chance at capturing long-term change over a reasonable amount of time. And that's exactly what we've done. The picture on the right shows Hakai scientist Katie Pocock, who's deployed instruments at the Cermak hatchery in Little Bear Bay in Johnstone Strait in November 2020 with the aim of capturing long-term change. However, without long records to detail what the long-term rates of long-term change are, we rely on estimates of anthropogenic CO2 and evaluations of what change has been over the industrial era to the present and to points in the future. We do this by using the delta TCO2 approach to estimate anthropogenic CO2. With this approach, we can calculate TCO2 for a given year with the inputs of contemporary alkalinity, temperature, and salinity, and calculate what the hydrogen ion concentration, pH, and saturation state levels are for that corresponding year. We can also consider points in the future. In this case, we considered at atmospheric CO2 level that corresponds with the full exhaustion of the 1.5C remaining carbon budget. This is the amount of CO2 that we can emit and stabilize warming to a particular level. In this case, the preferred target of 1.5 C warming in the Paris Agreement, what we refer to as the 1.5 C acidification level. The anthropogenic CO2 that we estimate has a broad range from 10 to 66. Values are shown in the upper right. The higher values are consistent with estimates of North Pacific surface water from Brendan Carter and Richard Feely and others. The lower values occur in areas of high glacial melt input. You can see that in the northern end of the transect, as well as in areas of mixing. In considering change over the pre-industrial to present time, we looked at the year when the first year when omega less than 1 would have emerged from the time series, and that's shown in the figure on the lower right. What this illustrates is that some areas likely have had corrosive saturation state conditions over the entire pre-industrial era, namely in Johnstone Strait, at least on a seasonal basis, but other areas have emerged, have had corrosive conditions emerge during winter more recently, namely the Salish Sea between 1915 and 1980, and in Southeast Alaska more recently around 2000. Finally, we can estimate the contemporary and 1.5 C acidification levels. We do this in terms of hydrogen ion concentration and saturation state on the left and right. The contemporary acidification level is shown across the top, and the 1.5 C acidification level is shown across the bottom. The contemporary change in hydrogen ion is on average about 40%, but you can see it varies regionally, with Johnstone Strait really standing out as a hot spot. The average pH change is 0.14. The 1.5 C acidification level is equals an increase of roughly 17%. The saturation state changes to the contemporary are about 0.4, and the 1.5 C acidification level change, it rises to about 0.55. But again, with regional variability, and I want to point out the seasonal variability, where it looks like there's larger saturation state changes during summer, as opposed to larger hydrogen ion and pH changes during winter, which makes sense, as the winter season would be when more weakly buffered seawater is present. And so in closing, partnership with the Alaska Ferry Service has allowed us to document variability over the 1,600 kilometer inside passage. The seasonal cycle dominates, with the roles of tidal mixing and net community production and freshwater input really determining the seasonal amplitude. We've characterized the extremes based on variability and severity, and can show differences and severity specifically shows differences that may have biological implications, as well as assessing the variability may help strategize our observing efforts. We've calculated anthropogenic CO2 as well, and shown that there's large regional variability. We've considered that there's areas where there's been recent emergence of saturation state less than 1, and we've estimated the contemporary and 1.5 C acidification levels, highlighted their seasonality, regional hotspots, and the significant change even with the best case scenario. I want to just close by saying, coming in late 2021, we have a new vessel that we've outfitted, the motor vessel Seaspan Royal, pictured on the upper right. This is a tugboat that operates in coastal BC. It operates along the lines shown in red, and we will have full seasonal coverage along those lines and in many areas where we have not had measurements before, so we're very excited by this. Final note, British Columbia Fisheries and Aquaculture Ocean Acidification and Hypoxia Action Plan is underway. This is a new endeavor led by the province to determine the state of knowledge related to ocean acidification and hypoxia in BC's coastal waters, with the long-term goal for developing mitigation and adaptation strategies to support fisheries and aquaculture sectors. There'll be a number of workshops over the next months to gather information from the community, the first of which will be a State of the Science workshop in November, that we hope many of the, all of the BC researchers can come and contribute. For more information, please reach out to Alex Clancy. And with that, I will wrap up. Thank you.